Read Fatma from base chemistry. Uh, I am going to present the second part of my presentation, which is racemic mixtures and resolution of enantiomers. Pasteur took an optically inactive tartaric acid salt are found that he could crystallize from it two optically active forms having the 2R3S and 2S3S configuration. But what was the optically inactive form he started with? It couldn't have been mesotartaric acid because mesotartaric acid is a different compound and cannot be interconverted with two chiral enantiomers without breaking and reforming bonds. The answer of this question is Pasteur started with a 50-50 ratio mixture of the two chiral tartaric acid enantiomers, and such a mixture is called a racemic mixture or racemate. Racemic mixtures are often denoted by symbol R or by prefix de to indicate that they contain equal amount of dextrorotatory and levorotatory enantiomers. Some mixtures show no optical activity because the rotation from one enantiomer exactly cancels the rotation from other. Pasteur was able to separate or dissolve the racemic mixture into D and L R and S enantiomers. Unfortunately, the crystallization technique he used doesn't work for most racemic mixtures, so other methods are required. The most common method for resolution is used as an acid-base reaction between racemic mixture of chiral carboxylic acid and an amine base to yield an ammonium salt. Carboxylic acid and amine base are react with each other and form the ammonium salt. To understand how this method of resolution works, let's see when a racemic mixture of chiral acids such as positive and negative lactic acid reacts with a chiral amine base such as methylamine. Stereochemically, the situation is analogous to what happens when left and right hand chiral pick up a chiral, but left and right hand pick up the ball equally well, and the products are mirror image. In this way, both positive and negative lactic acid react with methylamine equally well, and product is raised to a mixture of enantiomeric methyl ammonium lactate and methyl ammonium lactate. This is the structure in which racemic lactic acid, which contains 50% R configuration and 50% S configuration. When both R and S lactic acid configuration molecules are react in the presence of CH3NH2, then it forms the enantiomer racemic ammonium salt. These are the R salt and S salt are both are the enantiomers. They are not mirror images, but they are similar but different. The two salts are diastereomers and they have different chemical and physical properties. It may therefore be possibly to separate them by crystallization or some other means. Once separated, acidification of two diastereomeric salts with HCl then allows us to isolate the two pure enantiomers of lactic acid and recover the chiral amine from further use. That is this, the original racemic mixture has been resolved. Then in this structure, R configuration of lactic acid and which is 50% and S 50% S configuration of lactic acid is react in the presence of phenyl ethylamine, which forms the OR salt and SR salt, which are both are the diastereomers of each other. Then we talk about the isomerism. A brief review of isomerism is first, what are isomers? Isomers are compounds that have same chemical formula but different structure formula. Isomers is of two types, constitutional isomers and stereoisomers. Then stereoisomers is further classified into enantiomers and diastereomers, and diastereomers further classified into configuration diastereomers and cis-trans diastereomers. There are two different types of isomerism, both of which now encountered constitutional isomerism and stereoisomers. Constitutional isomers. Constitutional isomers are compounds whose atoms are connected differently. Among the kinds of constitutional isomerism we have seen are skeletal, functional, and positional isomers. First, uh, first is the skeletal isomers. Skeletal isomers are whose atoms are connected differently, and 2-methylpropane and butane are the skeletal isomers. And the functional isomers are ethyl alcohol and dimethyl ether. And the third is positional isomers. Positional isomers are isopropyl amine and propyl amine. Then is the stereoisomer, which is the second type of isomerism. Uh, Stereoisomers are compounds whose atoms are connected in the same way but with different spatial arrangement. Among the kind of stereoisomers we have seen are enantiomers, diastereomers, and cis-trans isomers. Cis-trans isomers are found both in alkanes and cycloalkanes. Cis-trans isomers are just special kind of diastereomers because they are non-mirror image of stereoisomers. These are the examples of isomers. First is enantiomers. Enantiomers are non-superimposable mirror image of stereoisomers, and it contains R configuration of lactic acid and S-lactic acid. And diastereomers are non-superimposable, non-mirror image of stereoisomers. And its examples are 2R3S, 2R3R 2 amino 3 hydroxybutanoic acid, and the other is 2R3S 2 amino 3 hydroxybutanoic acid. These are also called the configurational diastereomers because they are the non mirror image of each other. Cis-trans diastereomers are in this cis atoms are in parallel way, and the other in trans form, one atom is on one corner and the other is in the other corner. Substituents on same side or opposite side of double bond or ring. Then the other topic is chirality in nature and chiral environment. Although the different enantiomers of chiral molecule have same physical properties, they almost always have different biological properties. For example, enantiomers of lemon has the order of oranges and lemons, but the enantiomer has order of pine trees. These are the structures of lemon. Positive lemon is present in citrus fruits and negative lemon in pine trees. More dramatic examples of how a change in chirality can affect the biological properties of molecules are found in many drugs, such as fluoxetine, a heavily prescribed medication sold under the trade name Prozac. Prozac. Racemic fluoxetine is an extraordinarily effective antidepressant, but it has no activity against migraine. The pure S-enantiomer works markedly well in preventing migraine. Other example of how chirality affects biological properties in interlude chiral drugs. This is the structure of fluoxetine, which prevents migraine, and its configuration is S configuration. Then the other question is, why do different enantiomers have different biological properties? Because biological receptors are chiral, only one enantiomer of a chiral substrate can fit it in it. Just as only a right hand will fit into a right hand glove, the mirror image enantiomers will be misfit like a hand left hand in right hand. Enantiomer fits the receptor perfectly, but other does not. When an achiral substrate interacts with the receptor, green color of hydroxyl and gray color of methyl substituents of the substrate are held appropriately, but only the blue hemoglobin hydrogen AP hydrogen substituent is also held, while the red hydrogen is specifically exposed for removal in oxidation reaction. This is the whole process when ethanol reacts with NAD plus in the presence of yeast alcohol and dehydrogenases into acetaldehyde plus NADH2 molecule is formed. And the other is the green and gray substituents are held appropriately, but blue hydrogen substituent is also held while red hydrogen is specifically exposed for removal in oxidation reaction. CH3 is bound in receptor and 8P is bound in receptor. H2 is exposed for reaction. OH is bound in receptor. The receptor provides a chiral environment for substrate. In absence of chiral environment, the red and blue hydrogens are chemically identical, but in presence of chiral environment, they are chemically distinctive, so that only one of them, which is red color, is exposed for reaction. In fact, in effect, the chiral environment transfers its own chirality to a chiral substrate. Then the summary of the whole of the stereochemistry topic is um, a molecule that is not identical to its mirror image is called chiral molecule, and the usual cause of chirality is in the presence of a tetrahedral carbon atom bound into four different groups are called chirality center, and the chiral compounds can exist as a pair of mirror image stereoisomers called enantiomers, which are related to each other as a right hand is related to left hand. When a beam of plane polarized light is passed through a section of solution of pure enantiomer, the plane of polarization is rotated and compound is said to be optically active. If a curved arrow drawn in the direction of decreasing rank for remaining three groups is clockwise, the chirality center has R configuration, but its direction is counterclockwise, then the chirality center has S configuration. And the difference between enantiomers and diastereomers, enantiomers have opposite configuration at all chirality center, but diastereomers have same configuration in at least one center, but opposite configuration at other. Then the other three mechanisms are mesocompounds contain chirality center but are achiral overall because they contain a plane of symmetry. Mesocompounds contain chirality center and contains a plane of symmetry. And racemic mixtures are 50-50 ratio mixtures of positive and negative enantiomer R and S. The racemic mixtures and individual diastereomers differ in both their physical properties and their biological properties and can often be resolved.